How does an airplane really fly? One of the amazing things about modern aviation is the ability to generate enough force to put such massive planes in the sky. This can be seen in our observation video of a C-5 Galaxy aircraft taking off. The C-5 Galaxy has a weight of over 170 tons, but is still able to generate enough forces to take flight. After viewing this video and doing some brief research on the forces acting on an airplane, we were able to generate our hypothesis. Our hypothesis states that the difference in pressure across the wing creates drag and lift forces. These forces, along with thrust and the weight of the plane, are the forces acting on the plane, and they allow the plane to fly. In order to test this hypothesis and arrive at a conclusion, we conducted further research on the forces acting on an airplane.
When in flight, there are four main forces that act upon the plane. These forces are weight, lift, thrust, and drag. Weight is the force of gravity acting downward toward the center of the Earth. This force opposes the force of lift, which is created by differences in air pressure and is directed upwards and opposite of the Earth's center. In order to calculate lift, one must know the lift coefficient, density, reference area, and the flow velocity of the plane. The two opposing horizontal forces are thrust and drag. The thrust force also consists of multiple variables, including velocity and change in mass flow, and the drag, which is similar to the equation for lift, consists of density, reference area, flow velocity, and the drag coefficient. In a situation where a Boeing 737 has a mass of about 49,900 kilograms, it will be calculated that in order for the plane to take flight, the lift force required must exceed 489 kilonewtons.
As we analyze the forces acting on the plane, we notice that in each direction, rising, staying level, or declining, the horizontal forces stay the same. This is because that the plane is always moving in the forward direction. Now, as we analyze the vertical forces, we notice that whenever the force lift is greater than the weight force, the plane tends to rise. And when the lift force is equal to the weight force, the plane is level. And then when the lift force is less than the weight force, the plane tends to decline in altitude. The thrust and the drag force only determine the speed of the plane in the direction of the thrust force. This is because the plane is always moving forward.
Next, we study the physics of airflow across the wings of an airplane. The cross-sectional shape of the wing, called an airfoil, is key when considering lift and drag forces. As air flows over the airfoil, a low-pressure area is created above the airfoil, and a positive or high-pressure area is created below the airfoil. The low-pressure system is created due to the streamline velocity of the air increasing as it passes over the wing. The difference in pressure between both areas creates the lift force that acts on the airplane. Air resistance caused by the airflow contacting the plane's body and wing accounts for the drag force on the airplane.
The lift force is perpendicular to fluid flow. It's created by the pressure difference. The high pressure area provides a much greater force than the lower pressure area, where the lower pressure area is due to a higher velocity going over the top of it. The lift force determines how high or how low the plane is going to be flying at, based on the angles it is flying at. Now the equation. The lift force is determined by the pressure times an area coupled with the shear stress times an area, and that each of those equate to forces which will result in perpendicular forces. The coefficient of the lift force equals the lift force over 1/2 times the density times streamline velocity squared times the area. The coefficients of lift and drag are Euler numbers and are functions of Reynolds numbers and Froude numbers. The drag force is parallel to flow. When the fluid is moving at a velocity and hits a stagnation point, where velocity goes to zero, the pressure increases a lot. This pressure applies a force over an area that is trying to slow the plane down. The drag force is important to be able to calculate so that we know how much thrust is necessary. For the drag force equation, there's a pressure times an area coupled with a shear stress times an area, just like the lift equation, but it's all parallel to flow. An increase in surface area will result in more drag on a plane, but if more surface area is added to the airfoils, then more lift can be generated, so it's kind of a trade-off.
Throughout our research, we found that our hypothesis was true and that there are four key forces that make a plane fly. The thrust force must overcome the drag force in order for the plane to take off. The lift force is created by airflow over the airfoil, and it allows the plane to lift up and overcome the force of the plane's weight.